Hello class, this is section 6.3 and in this video we are going to discuss simple stability analysis using product solutions. In a previous video we were able to write down the product solutions of our partial difference equation here, FJGM, and we got our product solution UJM equals sine n pi j over n, big N, times 1 minus 2s plus 2s cosine n pi over big N raised to the nth power. And this is something we did not do in the previous video, but we will discuss in class. It turns out that it suffices to just take the n as 1, 2, 3, and so on until n minus 1. That there's no use going any further. You can see a little bit why. If you plug in little n equals big N, we get sine pi j, which is going to be equal to 0. So that gives us a trivial solution. So we just have to check from 1 to n minus 1. So these are our product solutions. Let's call this UJN as the product solution, the nth product solution. And since our difference equation is homogeneous, we can write down a solution of our partial difference equation as a sum of these product solutions. So this is going to be the sum of uj, n, m. Or in other words, this sum. So remember, our goal in the beginning of this section is to avoid this phenomenon called instability. Sometimes when we use partial difference equations to approximate differential equations, our solution can blow up if our S is too big. And our goal here is to determine how big our S has to be, how small our S has to be. So let's look at our product solutions. And it's clear here that blow up happens when this 1 minus 2s plus 2s cosine n pi over n term has an absolute value greater than 1. So remember that m here is the time variable. So if this thing that is exponentiating becomes larger than 1, clearly the solution will blow up in time. So we need to avoid this situation. So we can of course rewrite this 1 minus 2s bracket 1 minus cosine greater than 1. You can factor out the 2s from the last two terms. And this gives us a certain amount of insight. So remember that cosine is always between 1 and minus 1. So it means that this term over here is always going to be positive, which means that the minus 2s term is always going to be negative. And in particular, we know that this cannot exceed 1. So the only way that we can, the absolute value can be larger than 1 is if 1 minus 2s, 1 minus cosine, is smaller than minus 1. That's the only failure condition. And this is the only inequality that we need to avoid. So let's solve for s here. And we only need to avoid s being greater than 1 over 1 minus cosine n pi over n. Let's phrase it positively instead. Our solution, UJM, is going to be stable. It's going to avoid blow up if s is less than or equal to 1 over 1 minus cosine n pi over big N, for n equals 1, 2, 3, and so on until n minus 1. And it turns out that the worst case scenario is when n equals n minus 1, capital N minus 1. That's because that's the value that gives you the largest negative number for cosine is when n equals capital N minus 1, which means that we can just look at the worst case scenario. We have stability if s is less than or equal to 1 over 1 minus cosine capital N minus 1 over n pi, because that's the worst case scenario. And we can actually give some insight over it. So remember that cosine is always between 1 and minus 1. So this can never be smaller than 1 over 2. So s greater than 1/2 is always stable. And this gives us a good insight. And this means that we know that as long as we keep our s, and s, remember, is our k, delta t over delta x squared, as long as we pick our mesh sizes, delta t and delta x, so that s is less than 1/2, we are safe. Blow up can never happen. And we have stable solutions for this regime in S.